for another quick video, I would show you basically walk you through how I'm consuming research on this emerging topic. So I know when I was first starting, it was really helpful for me to be able to just witness how experts consume literature, how they go about confirming results, how they kind of decide whether or not they trust something or not. And a lot of that for me is basically reading how numbers are calculated and then trying to kind of reproduce those results myself. And so I thought as an example, I'd walk you through just a single estimation of a parameter that some folks from the CDC recently put out, and I would show you basically how I went through and read the paper, and then also how I was able to reproduce the results in R. And so this paper is in Emerging Infectious Diseases. This is the title is High Contagiousness and Rapid Spread of Severe Acute Respiratory Syndrome Coronavirus 2. And so this paper, this came out somewhat recently. It says here July 2020. So this is basically an early release of an article. So it came out maybe like a week and a half ago. So this is not the final version. They may be changing it along the way, but this kind of made a splash because it reported a much higher R0 value than has otherwise been talked about. And so the basic reproductive number, or R0, if you've been kind of consuming information about coronavirus or infectious diseases in particular, this is something that comes up a lot. And basically what it means is it's the average number of people a single infectious person will infect. And so if the R0 is 2, for example, that would imply that for every infectious person, they're infecting 2 more people. And so this particular one calculated a median R0 value of 5.7, which was a bit higher than what other people had seen before, and so it kind of was maybe cause for concern. And so what I wanted to do was sort of see if I could figure out where they got that information and how I could potentially replicate their finding. And so you can go ahead and read this paper. If you, I'll link to the paper in the outline, but you can also just Google this title: High Contagiousness and Rapid Spread of Severe Acute Respiratory Syndrome Coronavirus 2, and you can find it yourself. So the first thing I do if I'm trying to replicate a result is I go down to the methods, and often the methods will be described in some detail in the paper itself, but sometimes there'll be supplemental material that will describe it in much more detail. And so in particular for this, I'm just going to try to replicate this study covered a lot of different things, but I just want to replicate that single number just to sort of show you how I can do that. And so here, calculations of R0 and effective intervention strategies. So we considered realistic distribution of latent and infectious periods to calculate R0. We described the methods we used to calculate it in Appendix 2. So this is all the methods that we get in the full paper, but we can actually look at the appendix to be able to find more information about this. And so if we scroll to the top, we can see if we can find where Appendix 2 is. Here it is. I can click on that, and it's going to download the appendix. So let's make this a little bit smaller so you can see it. All right. So here's the Appendix 2, and it details where they got their data, and it also details how they estimated the different epidemiologic parameters. And finally, if I keep scrolling down, I can find how they actually estimated R0. So here it is, calculation of R0 from estimated exponential growth rates. And so this is the equation that they used for R0, and it says, assuming gamma distributions for latent and infectious periods, they have shown that this Wearing et al. Here, so this other researcher has shown that the value of R0 can be calculated from estimating exponential growth rate R from an outbreak like this. So you can, so this gives me the equation that they used, and there's a number of things that I need to plug in. So I need to plug in 1 over sigma and 1 over gamma. So we've got, well, let's just look at the equation first. We've got an R here, we've got a sigma, an M, a gamma, another R, and an N. So the unique parameters that I need to figure out are R, sigma, gamma, M, and N. So it tells me here that 1 over sigma and 1 over gamma are the mean, latent, and infectious periods, and M and N are the shape parameters for the gamma distribution. And so here it tells me that they assumed that M was 4.5 and that N was 3, and that they picked these parameters R, sigma, and gamma. They said that they were independent, and they generated random samples according to the ranges defined in Appendix 1, Table 5. And they generated 10 to the 4th parameters and accepted those within a serial interval within the range of interest, and they computed the 97.5 and 2.75 percentile to get the 95% confidence intervals. Okay, so this gives us almost everything we need. I've got an equation here, and I've got a bunch of parameters. I know M and N, 4.5, and N is 3. And so all I need to do is get Appendix 1, Table 5 in order to compute R naught. So we're going to come back to that in a second. Let's go back here and download Appendix 1. Okay, so here's Appendix 1. It's a big Excel sheet. I see on the bottom here I can click on Table 5. And so what this tells me the parameter and ranges for each of the values. So I'm going to make these a little bit smaller so they fit in my window here so you can see all of the text that they have. Okay, so the parameters we need are R, sigma, and gamma. So R here is the exponential growth rate of the outbreak, and they're assuming that this is uniformly distributed between 0.21 and 0.3 per day. And the reason they did that was based on estimations that were in the main text. Those came from some data that they had from the original Wuhan outbreak. And then they have 1 over sigma. That's the mean latent period, so like how long the disease is latent. And they chose a uniform distribution between 2.2 and 6 days. And so here they estimate the mean incubation period to be between 4.2 and 6 days. The lower bound for the mean latent period is set to 2.2 to consider the possibility that an individual becomes infectious 2 days before symptoms are onset. And then finally, this 1 over gamma, that's the mean infectious period. They let that be uniformly distributed between 4 and 14. And that range is to incorporate a wide range of possible durations of the infectious period. So the mean, if the mean duration of infectious period is longer than 14 days, then you're going to end up underestimating the R naught value. Okay, so I'm going to use all of this information. What I'm going to try to do is reproduce their original result. So let's remind ourselves what that original result is. Let's go to so this is back at the paper. I'm going to look down in the results section. Estimating R naught. So they have a couple different versions of this derived here, but what I'm going to do is I'm going to just estimate this one here. And so it says to derive realistic values of R naught, we use previous estimates of serial intervals for COVID-19. The serial interval is estimated to be between 7 and 8 days based on data collected for the early outbreak in Wuhan. And so then down here it says these results suggest a serial interval of 7 to 8 days. With that interval, we sampled latent and infectious periods within wide biologically plausible ranges and estimated the median to be 5.8 with a confidence interval of 4.4 to 7.7. So let's see if we can reproduce that result. Okay, so the first thing I'm going to want to do here is I'm going to want to set up a number of simulations. And so I'm going to make a variable called nsim. And I'm going to make that 10 to the 4th since that's what the authors said they did in their... And then what other parameters do I need? So let's pull up that initial document to remind ourselves of what parameters we need. We need an R, an M, an N, a sigma, and a gamma. So let's start with the easy ones because we know that M is 4.5 and N is 3. So I'm going to go ahead and set those in R. And the next one I'm going to do is R. And so from this Excel table, it said that they picked R to be a uniform distribution between 0.21 and 0.3. So in R, there are these cool functions called that are called, basically they let you randomly generate data. So there's one called RUnif, which basically lets you sample from a random uniform distribution. So I can pull this over if I do $RUnif. These functions provide information about the uniform distribution on the interval from min to max. And so I can plug in n, the number of samples I want, and a minimum and a maximum, and it'll give me a distribution of a random distribution of uniform variables. And so in this case, I want it to be between 0.21 and 0.3. And so I'm going to do nsim is my number of simulations, and I want this to be 0.21 and 0.3. Oh, we got to make sure I run everything first. And so let's see. So this gives me, I've got now 10 to the fourth, so 10,000 values, and these are all random values between 0.21 and 0.3, and it's uniformly distributed. And so I can look at this as a histogram. And it looks like a uniform distribution. So uniform distributions, basically you expect it to be uniform across the whole range, and you expect my minimum to be 0.21, which it looks like it is, and my maximum to be 0.3. So it looks like it worked. So that's how they generated R. The next one I need is sigma. And so they said sigma was equal to 1 over 2.2 to 6. There we go. And now the last one is gamma. Which was from 4 to 14. So now the final thing I need to do is I need to type up that whole R naught equation. So let's look at that real quick. So here's that equation. That's what I'm going to be replicating in R. So I've got my exponential growth R times R over sigma times m plus 1 raised to the m. That whole thing divided by gamma times 1 minus R over gamma n plus 1 to the negative n. So let's get that into R. R naught, so it's going to be R times R over sigma times m plus 1, and then that quantity raised to the m. And then it's going to be divided by gamma times 1 minus R over gamma times n plus 1. That quantity raised to the negative n. Great. Awesome. So now I've got a whole bunch of R naught values. And so now what I need to do is I need to pick the median of that. So I can just use the median command that you already know. And I get 6.9. So that, wait a second, I think that that's way higher than what we were looking at in the original paper. So there must be one other step that we're not doing yet. So let's go back to the text. And it says here that they used previous estimates of serial intervals, and they estimated them between 7 and 8 days to be collected during the outbreak. And so basically they sampled latent and infectious periods within a wide biologically plausible range, and then subset to just specific serial intervals. So the serial interval, it turns out you can estimate that, and on this you can just trust me if this is how you can estimate a serial interval, but basically you can estimate it as equal to 1 over sigma plus 0.5 times 1 over gamma. And so what that basically means, if you can remind yourself what the 1 over sigma, so 1 over sigma is the latent period, 1 over gamma is the infectious period, and so that serial interval is basically the latent period plus half of the infectious period. So that's what that is. And so what we want to do is we actually want to subset our R0 values to be just the ones that fall within the serial interval less than 7 and the serial interval actually greater than 7 and the serial interval less than 8. So you want to pick just the ones where the serial interval is between those values, and we want to get the median of those. 5.86. Great. And then the final thing we want to do is take the 95% confidence interval, and so we can actually just use the quantile function, and we can even, instead of having to do this in 2 separate steps, we can just do 1 because quantile can also calculate the median. And so we want the 0.025, the 0.5, and the 0.975 quantile. So that has 4.4, 5.86, and 7.8. Let's check and see what the original results were. 5.8, 4.4, and 7.7. That looks pretty close. It looks like we've got slightly bigger here. So let's see if we ramp up our simulations if we end up getting a slightly different result. So when we ramped up our simulation, this ended up coming down to 5.8, so it was much closer to that original one instead of 5.86. And so you can see that there's some variability in each of these runs. This one ends up with 5.88. This one is 7.76. And so this is important. I think one thing to keep in mind here, and something that I'm trying to work on some write-ups on, are kind of all the different places that uncertainty creeps into these different models. And so the fact that they're doing a simulation means that they've taken into account that there's uncertainty in these parameters. And so if they had been, for example, if they had just picked the middle value of each of these parameters, they wouldn't be accounting for that uncertainty. And so that's one place of uncertainty. And the other place of uncertainty is just when you do a random process, you're going to get slightly different values every time you do it, unless you do a really, really big simulation. For example, if I ramp this up to 10 to the 6th and I run it, if I run it 2 times in a row, the answers are going to be markedly similar between each other. And that's because as you ramp up your simulations, you get less of this kind of stochastic error along the way. So I hope that was helpful to give you a little bit of an idea of kind of how you can dig into the research and kind of figure out what's going on under the hood. Please post in Gitter if you have any comments or questions, or if you're reading something that's epidemiologically related that you would like some input on. I'd be happy to give some insight.